Hello, welcome back to the lecture series in wave optics. In last lecture we have discussed the basic concepts of diffraction phenomena, and then we recall the concept of Huygens theory, Fresnel assumptions. Again we discussed how the rectilinear propagation of the wavefront using the can be explained using the Huygens Fresnel assumptions. In Fresnel assumptions, we have studied that a wavefront can be divided into large number of small half period zones, and every consecutive zone send wavefront of pi phase difference and lambda by 2 path difference. Now, in this lecture we will discuss how we can practically demonstrate the Fresnel half period zone. This can be achieved by constructing a zone plate. Now, a zone plate is a specially constructed screen such that light is obstructed from every alternate zone. The correctness of the Fresnel method in dividing the wavefront into half period zones can be verified with its help. Now, this is the zone plate. Now, a zone plate is a screen such that the light is obstructed from every alternate zone, and it has a concentric circle with the equal area. You see here there are concentric circles are there, and the condition of this zone plate is the radii of these rings are proportional to the square root of the natural numbers. Now, what is a simple way to construct a zone plate? For this, let us draw a concentric circle on a white paper. Remember that the radius of that circle should be proportional to the square root of the natural numbers. That means, the odd numbered zones like first zone, third zone, fifth zone, etc., are covered with the black. First zone, third zone, fifth zone, etc., which are covered with the black ink. And let us take a reduced photograph of that, which appears in this particular figure. This is the concept. So, the odd zones we have are with the black ink, and the even zones are with the white background. Now, let us take the negative of that photograph. So, the negative of the photograph, it look like this, negative of that this photograph. Here the odd zones are transparent. Now, you see in the negatives that will be like the odd zones are transparent and the even zones will be opaque here. So, the odd zones means the first zone which is transparent, third zone, fifth zone, seventh zone, etc., which are transparent. The even zones second, fourth, sixth, etc., which are opaque. So, this is the simple way to construct a zone plate. So, now this is a zone plate. So, a negative that is transmitting light through its odd zones. Let us see what happens when we held this zone plate perpendicular to the incident beam of light. Now, this is the zone plate which I placed in front of the light. Now, the light pass through the zone plate and an image formed in front of the on the screen. You see image formed on the screen at the other side, and let us consider we observe the maximum brightness is possible at some position on the screen, say at a distance b. Assume there is a screen over here. Now, at this particular point on the screen, we assume we are getting the maximum brightness, and which is at a distance b. centimeter from the zone plate. In order to understand it clearly, let us draw the upper half of the wavefront part. Upper half means just I am considering this part only. Now, if I consider this in 2 dimensional, then initially I have a transparent region here, then I have an opaque region here. So, this is an opaque region, then again another transparent region over here, then opaque, and so on. So, OX is the upper part. So, 2 dimensional diagram of this zone plate, here it is drawn on OX. Now, P is a point here, now which is at distance B, where P we are getting the maximum intensity. Now, the distance of that P from the wavefront is obviously B. Now, we are assuming a wavefront, a plane wavefront is incidenting here. So, the first part OM, that is acting as a transparent region to that wavefront, will be focusing to P, and again M1 M2, this is the second part, that is acting as the opaque region to this particular wavefront, again transparent, opaque, and so on. Let us consider this distance OM1, OM1 as R1. OM1 means what exactly it is? OM1 is the radius of the first zone. Then again OM2, OM2 means from here to here, this is the radius of the second zone here. And etc. These are the radius of the zones. So, R1, R2, R3, etc. As we have already discussed in the previous lectures, these radius are proportional to the square root of the natural numbers. Therefore, again from the derivation of the last lecture, we know that this R1 is equal to root B lambda, and again you can write R2 is root 2 B lambda. Here this each radius are proportional to the square root of natural numbers, where B lambda is constant, and so on and so on, and the radius of the nth zone Rn can be written as root of n B lambda. So, from this you can have the equation for distance B from the wave front to incident wave front to point P is, that is a distance B, that B is equal to, just I am taking the square of this one. So, I will have the equation Rn square is equal to n B lambda, then you can easily have the value of B is Rn square divided by n lambda. So, if the source is at a large distance from the zone plate, the brightest spot will be obtained at point P. Here the even number of zones cut off the light, you remember that they are out of phase, you remember it. Since 2 consecutive zones produces the path difference of lambda by 2. What I mean to say, the wavefront from the first zone and wavefront from the second zone, they are out of phase and they are with the phase difference lambda by 2. Then the wavefront from OM1 first zone is in up direction supposed to be, then the next zone is in the opposite direction, opposite phase. So, they will be getting cancelled out. But since alternate zones are opaque, since therefore, what you will have, the net amplitude of the wavefront reaching at point P, that means the light from here and light from here, these are in phase, or the wavefront from the first zone and the wavefront from this particular zone, these are in the same phase. Therefore, the net amplitude A is equal to, net amplitude at point P A is equal to, let me say M1 is amplitude from this particular region. Again let me consider M2 is the amplitude from this particular region, and we will have another odd region where the amplitude again in the same phase, let me take it as M3, and so on. So, all the amplitudes are getting add up. Now, this is something like the light is converging to a point P here. Therefore, in this case the distance B can be taken as the focal length of the zone plate, and this zone plate, the focal length of zone plate, just let me denote with Fn. So, the equation for Fn is focal length Fn is equal to Rn square divided by n lambda. So, this is what this is what the equation. So, this we have taken it as focal length of the zone plate, Rn square divided by n lambda, where n is equal to 0, 1, 2, 3, 4, etc. The focal length here depends on lambda, that is the zone plate has different foci for different wavelength, and larger the wavelength, the focal length will be again longer. What it is very interesting here, that as the even number of zones are opaque, the intensity at point P is much greater than that when the whole wavefront is exposed to point P. In the first case, what happened? In the first case means the even number of zones are opaque. That means the total amplitude A is, you remember, basically A should be m1 minus m2, right. This is the amplitude from the first region, this is the amplitude from the second region, then plus m3 minus m4, this is the amplitude from the fourth region which is out of phase with m3 and m1 and so on. But you remember, in the first case the half zones are opaque means even zones are opaque means this m2 is getting cut off, m4 getting cut off and m6 is getting cut off, only you will be getting m1 plus m1 plus m2 m3 plus m5 plus m7 etc. That means the intensity amplitudes are getting add up. Remember, n is supposed to be an odd number. Now, what happens if when the whole wavefront is unobstructed? The equation should be in this way: A is equal to m1 minus m2 plus m3 minus m4 plus m5 etc. If n is odd number, we have already been discussed that the amplitude should be approximately, not approximately, it is equal to m1 divided by 2, that we have discussed. Here the amplitude is m1 by 2, it is small and its intensity will be small. So, when we have the opaque region with the odd number of zones, if the odd number of zones are opaque, we will be getting much greater intensity. If a parallel beam of white light is incident on a zone plate, the different colors comes to focus at different points. That the function of this zone plate is very similar to that of a convex lens. A converging lens, it is a converging lens. When the light is incidenting on a zone plate and that is converging to a particular point with a focal length, but the focal length, the equation for focal length, that depends on wavelength of light. That is, there is a formula connecting the distance of object and image point in case of a zone plate also. Well, now let us consider the action of zone plate for an incident spherical wavefront. Here consider S is the source of light and P is the position on the screen. Assume there is a screen over here, assume there is a screen here. So, P is a position on the screen where we are getting a bright image. Now, here A is the object distance, that means from source to zone plate, then B is the image distance, that is the distance between plate and screen. Here there are different zones are there, one transparent zone, then opaque zone, then transparent zone, then opaque zone and so on. Here OM1 is the radius, OM1 is the radius of the first zone, that is equal to R1, and OM2 is R2, OM2 is R2, that is the radius of the second zone and so on, radius of third zone, radius of fourth zone, etc. Then OMN, that will be giving you the equation for Rn. Now, the position of the screen is such that from one zone to the next there is an increase of path difference by lambda by 2. So, you have arranged. So, from the light wavefront from one zone and another zone, then there will be a path difference of lambda by 2. Well, so we have discussed that A is the object distance and B is the image distance. Then SO plus OP, SO plus OP is equal to A plus B. Now, let us take SM1, SM1 plus M1P, that is SM1 plus M1P, that will be giving you A plus B plus lambda by 2, because in every zone there should be a phase difference of path difference of lambda by 2. Then if you take SM2 plus M2P, SM2 plus M2P will be giving you A plus B, and we should have 2 lambda by 2 path difference, then plus 2 lambda by 2 and so on. The next will be SM3 plus M3P will be giving you A plus B plus 3 lambda by 2. Now, let us consider a triangle SM1O. From SM1O, so this is the triangle. Here this radius is R1, the base length is A. So, SM1 can be written as square root of SO square plus OM1 square by using the simple theorem. So, SM1 is equal to SO is A and OM1 is R1 square under root. Similarly, you can on the other side OM1P, what is a triangle? O here, M1 here, this right angle triangle. So, from this right angle triangle M1P can be written as root of OP square plus OM1 square. Now, here OP is B. So, B square OM1 square is R1 square. So, we will have the equation for SM1 is equal to root of B square plus R1 square, and this formula I have just put it with the equation number 2 and this is with the equation number 3. Well, now substituting equation number 2 and 3 in equation number 1. So, the equation number 1 was here, then I can have the formula SM1 plus M1P is equal to A plus B plus 2 lambda by 2. So, this was the formula. Now, I have substituted the value of SM1 and M1p here. SM1 was root of a square plus r1 square, here it was root of b square plus r1 square, and that will be equal to a plus b plus 2 lambda by 2. Now, I took a as a common factor from this one, then that will be root of 1 plus r1 by a2 r1 square by a square, plus here I took b as b square as common factor, then which when it comes out of the square root, then it will be b root 1 plus r1 square by b square, that is equal to a plus b plus 2 lambda by 2. So, this I can expand as a into 1 plus r1 by a square. You can square root of, you will have square root of 1 plus r1 square by a square can be approximated as 1 plus r1 square by a square. Now, I am multiplying here it with a, here it with a, then I will have a plus r1 square divided by a. So, this is the term I wrote here. Similarly, this also can be expanded like this. So, b plus r1 square by b, on the right hand side we have a plus b plus 2 lambda by 2. So, here it is a plus b is there, here it is also a plus b is there, getting cancelled out, then the remaining term is r1 square by a, then here it is r1 square by b, and the left term here it was 2 lambda by 2. So, here r1 can be taken outside as a common factor. So, r1 square into 1 plus 1 by a plus 1 by b is equal to lambda. Yeah, this was the formula we were having in the last slide. R1 square into 1 plus 1 by a plus 1 by b is equal to lambda it was. So, instead of R1 I put it here Rn. When I am substituting here Rn, then here it should be the number n lambda. So, Rn square into 1 by a plus 1 by b is equal to n lambda. Now, we need to give the sign convention, because we have two measurements from here, one is toward this side, one is towards the left hand side and another one is towards the right hand side. So, A is taken towards the left hand side and B is taken in the right hand side. We have to apply, therefore, we have to apply the sign convention. So, we applied the sign convention. Here I put minus b here. So, in r n square is equal to 1 by a minus 1 by b, it should be equal to n lambda. Or you can rearrange this formula as 1 by a minus 1 by b is equal to n lambda divided by r n square. You just recall that we have discussed that the focal length f n was r n square divided by n lambda. Therefore, n lambda by r n square can be written as 1 by f n, that is the focal length of the zone plate. That is, it is similar to the equations we have already have, that is 1 by u plus 1 by u minus 1 by v is equal to 1 by f, and this formula is very familiar to us. That is the equation for the focal length of a convex lens. Here u is the object distance and v is the image distance. Instead of u and v, we in zone plate we have a and b, and you remember a is the object distance and b is the image distance, and f n is the focal length. That means the zone plate act as a converging lens. But you remember the zone plate has number of foci, number of focus points, which depends on the number of zones used as well as the wavelength of the light I am blowing. Obviously, there are a few differences. Between the zone plate and the convex lens. Initially, for a convex lens has only one focal length, and you know the equation for that focal length was f is equal to 1 by f is equal to mu minus 1, that is the mu is the refractive index, and into 1 by r1 minus 1 by r2, where f is the focal length of the lens. Obviously, mu is the refractive index and r1 and r2 are the radius of curvatures. In case of a convex lens, the violet ray of light comes near to the lens, and the red light bit far with respect to the violet. This is because for a given material the refractive index of the violet rays of light is much more than the red light. So, the concept is it has one focal point for a particular wavelength. Now, in case of a zone plate, there is number of foci between this point O and P. So, this is the one major difference. So, each focus corresponds to the position with respect to the point P, an odd number of half period zones which can be constructed on the constructed on each zone. Well, with the increasing the focal length of the zone plate, the brightness of the image decreases. Let the first zone contain only one period element, then the amplitude at point P is due to the zone is m1. Supposed to be only one zone, then the amplitude is m1. If the first zone contain 3 half period elements of a particular position on the screen, then the amplitude at point P is due to the first zone is A is equal to m1 minus m2 plus m3. You can write like that m1 can be written as m1 by 2 plus m1 by 2 and that minus m2 plus, now m3 again I am splitting into m3 by 2 plus m3 by 2. Now this m1 by 2. Okay. So, m1 by 2 plus m3 by 2, that will be giving the average of m1 plus m3 divided by 2, that is equal to m2, as we discussed earlier, because the amplitude is gradually decreasing. So, m1 plus m3 by 2 is giving you m2 itself. So, this will be getting cancelled out. So, this amplitude A, so this is not A1, this is A, this A is equal to m1 by 2 and this is left here and this term left here, m3 by 2. Here this m1 by 2 plus m3 by 2 that can be written as m1 plus m3 divided by 2. You know this is less than m1. So, earlier we were having the amplitude m1, here this amplitude we are getting less than m1. If we have single zone, then we were having m1 the amplitude. If we have the 3 half period zones, then we are getting lesser amplitude here. Again, another difference in zone plate and convex lens is in zone plate the focal length for the violet light is more than that for the red light, which is again the reverse in case of a convex lens. Obviously, if we compare between the zone plate and the convex lens, both the zone plate and convex lens form a real image of the object. This is a very common similarity between zone plate and convex lens. Then the focal length of both depends on the wavelength and suffer the chromatic aberration. The chromatic aberration in zone plate is much more severe in comparison with the convex lens. And another comparison is the zone plate act as simultaneously as convex lens and concave lens. In addition to the real image, a virtual image is also formed simultaneously in case of zone plate, and a convex lens forms only the real image. You may remember that. It depends on the position of the object as well. So, in case of a zone plate, the image is formed by the diffraction phenomena. In case of convex lens, the image formed due to the refraction of light. Then another when we compare the zone plate and convex lens, the zone plate has the multiple foci on either side of the plate, hence the intensity of the image formed will be less. That is a major difference here. And again, convex lens has only one focus as well as the light focus at one point, then the intensity of the image will be more. And zone plate can be used for a wide range of wavelength from the microwave to X-rays. The glass lens cannot be used beyond the visible region. So, these are the some comparison between zone plate and convex lens. So, with this I am summarizing here. So, we have discussed about the formation of the real formation or the practical formation of the half period zones through the construction of zone plate, and we have derived the formula for the focal length of the zone plate, and we compare this zone plate with the convex lens. With this I am ending today's session here. We will meet again in another session with another topic. Thank you.